Hello, nice little integral problem today. So we've got e to the x times dy dx plus a y squared is equal to xy squared. And we're told that it goes through the point 1e. So that tells us that we can actually find a particular solution using our coordinates later on. So first things, how are we going to solve this? What we need to do is kind of rearrange everything and spot that this is separable. So we're going to bring everything to one side and try and factorise. So for example, this y squared, let's subtract that from both sides. So that's going to give us e to the x times by dy dx is all equal to x y squared minus y squared. This side then we can factorise, take the y squared out the front, and it's x minus 1. Now then, when we look at these two parts, we can see that we've got all the y's and all the x separate. There's no point where they're kind of added together. They're always multiplied. I know we've got an x stuff over here, but again, that's not added to any y's at all. So what we can do is bring all the y's to the left-hand side and all the x's to the right. So we're going to divide by the y squared and divide by the e to the x. So what we've got there is 1 over y squared multiplied by the dy dx still, and that's going to equal x minus 1 all over e to the x. From here then, because this is separable, i.e. we can write the y's and the x's all separate, we can integrate by doing both sides separately. So this dx, we're effectively going to move it over here. The actual process is a bit more involved, but it ends up being always the same in the end, where we can think of this side having the dy, and I will write that y squared as y to the minus 2 now. And this side then will get the dx. So the x minus 1 is still there, and e to the x on the bottom like that. And now, because we've got dy and dx separate, we just do them as an integral and individually. They're not going to affect each other whatsoever. The y to the minus 2, nice and straightforward. Raise the power to minus 1. Divide by that minus 1 is the same as just dividing by, well, times it by minus 1. And that's going to equal something over here. This is a product of things. So we need to use by parts. So let's do that over here in the blue. Rewriting it very quickly, we have e to the minus x times by x minus 1. So we've got one bit that we're going to differentiate, one bit we're going to integrate. Whenever you have a polynomial thing, it's nice to set that as the bit you're going to differentiate. The reason being, if we look at that quickly, if we set u to be x minus 1, when we differentiate it, we just get 1. So when we actually do the by parts formula, and this gets times by v, we end up with just what v is by itself, so no longer a product. So we've simplified our integral into something that we can perform without by parts or substitution or something like that. So the v dash then has to be the e to the minus x, which when we integrate stays the same but becomes negative. So v is just negative e to the minus x. So sticking this all together, we'll have u times v, so minus e to the minus x multiplied by x minus 1, and then take away the integral of u dash times v. So like I said, this 1 now is really useful. So we've just got this thing by itself, this has a negative at the front, that negative there will combine together and will give us a positive, and then it's e to the minus x, again dx on the end. So performing that integral, what we're going to see is that this becomes just minus e to the minus x. I will also expand the brackets as in this negative in here. So this negative we're going to kind of distribute over the bracket there. So instead of it being x minus 1, we'll have 1 minus x in the bracket, still with the e to the minus x out the front. And what you can see now then, this has 1 minus x minus a 1. So this 1 and like this whole term end up cancelling out. So this entire thing, what does it equal? It's just going to be minus x e to the minus x. So we can use that now. We can sub that on this side. So what we're going to see is we have minus x e to the minus x. And because we've done an integration, we need a constant of integration. This is what we're going to use now alongside our coordinate to find the particular solution. This is a general solution. You normally would rearrange for y, but still this is a different form of a general solution. But now then, we can take our coordinate and sub it into the general solution to get the particular solution. The way to think about it is this is like a family of curves. So it's going to be like whatever shape it is. Imagine it's this sort of shape. You can imagine us having lots of those. And what the C does is lock it into one of these. It picks which one it's going to be on to make sure we go through that coordinate. These family of curves will never overlap. They'll always kind of just be side by side, kind of squashed together. The C gives us a coordinate. So it picks which one of those curves that we need. So doing that, let's just sub in the values we have. So It might be nice to rewrite this a little bit first as well. So that minus 1, well, minus y to the minus 1 is minus 1 on y. And on the other side, we've got a minus x over e to the x, and then plus c still on the end. So yeah, subbing everything in, what do we get? So e is going to be our y. So that's going to be minus 1 on e. And that's equal to minus x, so minus 1, over e to the x, so e to the 1, plus c. What we can see here, these two bits are the same. So there's no difference in them. C therefore is going to be 0 as well. C equals 0, not just 0. So what this can tell us, we can look back at our original function and actually plug in the value of 0. So what we have is just that thing, minus 1 over y is equal to minus x over e to the x. Those two negatives can cancel. They're multiplying everything on both sides. And now we want to get y by itself, so let's just reciprocate both sides of our function. So our final solution, y is equal to e to the power of x, all divided by x. Lovely jubbly.